We are still looking at acid-base equilibria. This is part 6. We are specifically going to just look at one example having weak acids, having to do with weak acids. And the example is 1.00 molar HF, and there is the Ka for it, 7.2 times 10 to the negative fourth. Going to go right through the steps on how you figure this out. You already know to write the major species. HF is a weak acid. It's not on the strong acid list. So since Ka is so small, the dissociation is so tiny, it indicates that HF stays mostly together when it's tossed in water. Therefore, the major species must be just HF and water. What about H+, F negative, OH negative? They're so tiny in comparison. Remember, that's what the Ka means, that we can discount them. There would only be a tiny, tiny amount of those in comparison to how much HF and H2O there are. So we can discount their presence. Now, write out the equations. You should be able to do that. There's two equations that might be relevant here since this is a weak acid. This is the first one, and there's the dissociation. And the second one is, of course, water. So you would write that out as well since you've declared them to be the major species. And there's the water dissociation. Now, for step 3, after you've written out the equations, I want you to analyze those Ks. Look at the difference between them. There seems to be a rather large difference between those two Ks. So what can you assume? In this case, HF's Ka is much larger than Kw. So you can ignore the effect from water, from the water dissociation, because it's so small in comparison. Step 4, write out the equation. Ka equals 7.2 times 10 to the negative fourth, which equals concentration of H+, F negative over HF, remember products over reactants. Step 5, list the initial concentrations. We're going to make like a chart and list the concentrations at equilibrium. So this is going to be like a little table. What was it initially? What was it at equilibrium? Initially, we had all HF at 1.00 molarity. We didn't have any fluoride ions or hydrogen ions. However, at equilibrium, since it's a balanced equation, we now have an X amount of fluoride, X amount of hydrogen, and 1 minus X for the HF. What do you do with that information? Well, plug it into the equation that you just had up above. That would be X times X over 1.00 minus X. However, since X is tiny, in comparison to the 1 molar, it can be dropped or ignored as well from the equation. So drop it from the equation and you can rewrite it without that minus X. Now solve for X. Now it's easy to solve for X and you don't have to go into quadratics. And so the molarity for that is 2.7 times 10 to the negative 2 molarity. If you're unsure about dropping the X, that would be step 7. So you use the 5% rule for that to validate. And here's the general equation for the 5% rule. X over concentration of HA at the start times 100 is less than 5%, then you can discard the X. All right, this one's yours. 0.100 molar HOCl. You go through all the steps. There's the Ka, and I want you to find the pH. And I'm not showing you any of them. Here comes the answer. Pause if you don't want to see it. Don't forget to validate. Here's the answer, 4.23. You go through all the steps and make sure you can figure that out. This is end of part 6. We are still looking at